remember, we're analyzing this thing called the sampling distribution. Every student's name and school is in this, and I want you to take out 20 and go get your sample mean. Where did we leave off yesterday? Wow. You know, the other class, we're all the way to there. Grab 20, get your 20 numbers down, and get your X bar. Okay, the three things that we want to analyze that we're going to take a look at in this thing called the sampling distribution is we want to check out what the center of it is. Weird symbol here. Let's see if we can kind of follow that symbol. The center of the sampling distribution, isn't the sampling distribution every possible X bar you can get? And I want to find the mean of all those X bars. Okay, weird symbol. In terms of the spread, what we're going to be trying to analyze is how spread out all the X bars are. So all these different X bars, I want to find out the standard deviation of all of those X bars. And then finally, I want to know the shape, what all those X bars shape is. Is it normal? Is it skewed left, skewed right? All those other things. So when I say describe the sampling distribution, these are the three things that we're going to analyze. All right, let's go back here to the work we've been doing. Follow me, okay? Taking notes. Okay, last period, we started building our sampling distribution. Okay, so these were the means that we got to for last period. Let's keep adding to it. Now remember, how many possible sample means are there for this problem? Does anybody remember that? 4.7 and then 46 more zeros. Okay, so are we going to be able to find them all? No way. Okay, and remember now, the number that you give me, that's the number you're going on television with. That's your only shot at this thing. So you're going to go on television with the number you give me and say, this is my prediction for the average length of name for all the students at Elk Grove High School. Remember that big bucket? That's these. Okay. All right, Bree, did you get a mean for me? This is yesterday's, working on yesterday's?
Yeah, I got
12.75. Let's just keep going. 13 point what? 25. And somebody over here, since you guys, start putting these numbers in if you can, your L1, as many as you can get in. 13.75. 12.75. This was somebody in 7th period yesterday, so we'll keep it up there. 12.9. 12.9. 12.9.
That's it.
12.9, good. 12.8. 12.8.
14.25.
14.25. Interesting. Okay.
12.5.
12.5.
13.25.
13.25. Thank you.
12.25.
12.25.
13.75.
13.75. 12.95. 10.65. Okay. All right. Now, as I said, is that all of the? Is that the complete sampling distribution? No way. Okay. But I do want to analyze at least what we've got. Okay. So as soon as you guys come up with a number, I would like to take the mean of all of these X bars. So that's the symbol. That's the symbol that's going to represent the center of our sampling distribution. Did we get a number for me yet? We don't have to enter all 4.6 times 10 to the 46. You've been getting close. You guys put it in your calculator so that for your class we can go quicker. 12.8. Cool, then we'll just go with that, okay? So it looks like that the mean of what we've got so far is around 12.81. All right, now, you should have learned something very important on problem number 7 last night. On one of those problems, didn't you find the entire sampling distribution? Didn't you find all 45 possible x bars? And what happened when you took the mean of all 45 of those x bars? What did it turn out to be?
The exact mean
Of the
of the 10. The 10 scores the mean.
Yes, so it's the exact mean of the...
Of the 10 scores.
No, what is that? The exact mean of the... Yes. Didn't the mean of all 45 of those x bars just so happen to be the mean of the population distribution? And that will always be the case. If we would get all 4.6 times 10 to the whatever of these, if we had them all, and we took the mean of all of them, it would happen to be equal to exactly the mean of the population distribution. Okay, so we know what this will be. Okay, the mean of the sampling distribution will be equal to the mean of the population. Okay. In fact, we have a special name for that. If we're looking at a statistic where the mean of the entire sampling distribution is equal to the mean of the population, we call that statistic an unbiased statistic. Now, is that important? There's a great illustration in your book. I think it's the best illustration your book's got. Go to page 500, and it's a bunch of dartboards. Now, the dartboard. The middle of the dartboard is, hey, you know, what is the true mean length of names at Elk Grove High School? That's the dartboard. That's what we're trying to figure out, right? Now, every one of those dart marks on the dartboard are these guys. Okay, now, do we want to be using a dartboard like letter A? I mean, all the predictions we get are horrible. None of them are even close to what I'm looking for. That's called a biased statistic. If you took the mean of all of those darts, they're not even close to what I'm looking for. I mean, don't we hope, I mean, you're going on television with this guy. Don't you hope it's a part of a world that's at least centered at the right answer? Yes, we want an unbiased statistic. So, that first one on A, that is a very biased statistic, right? The mean of those aren't even close. C is also a biased statistic. All of those darts aren't even close. I don't know, I'm guessing the average length of name is whatever that was, is probably close to 12 point whatever you guys said. I mean, I don't want these guys all at 20. Biased. What I'm looking for is a dartboard like B and D. Part B, okay, all of those darts, okay, are at least centered at the right answer. And then part D is even better. We'll talk about that in a second. All of those darts are centered at the right answer, and they're all really close to the right answer. Okay? Now, X bar. This particular statistic, X bar, this is always going to be the case. If you ever take a complete sampling distribution, now do we have a complete one here? No way, and not even close, right? But if you ever got the complete sampling distribution, like you did on number 7 last night, the mean of all those X bars will, in fact, be centered at the mean of the population, which is what we're looking for. Okay? All right, number 2. Let's start analyzing how spread out these guys are. The other big thing that I want you to come up with on number 7. You did 2 different types of problems, right? On one of them, you took a sample size of 4, and you found only 10 of them. And then I asked you to figure out how spread out those 10 were. And then I asked you to do a sample size of 2. You actually found all of them. And I asked you to see how spread out the sample size of 2 were. All right, this is the big deal now. Which one of these, the sample size of 4 or the sample size of 2, were closer together. Which one of them, the sample size of 2 or the sample size of 4, gave you a bunch of darts that were close together? I saw a hand. Yes. Did you guys get that? I don't know what was your, and these are all could be different because you took different samples of 10, but what was your standard deviation for the sample size of 4? 2. And then we all should have got the same standard deviation for the sample size of 2, like 2 point, or no, I'm sorry, 4, which is 5 point. Should have been 5 point something. 5 point. That's fine. But this is the big deal here, okay? This is huge. What will get these X bars closer together? Well, first of all, do I want the X bars closer together? Look at page 500 again. Which dartboard? Now remember, one of those little dart marks, that's you. Which one of those dartboards do you want to be dealing with if you're trying to predict the future with your one little dart? Do you want B or D? You want D, don't you? Because all of those are pretty close. So what can you do as a statistician? So I'm going to go and I'm going to try to predict something. What's a good thing to do? Take a bigger sample size or a smaller sample size? Bigger. Now you could have answered that walking in the door the first day. But now you know why. Because all of the possible X bars you can get are going to get more bunched together. And you should know that. Law of large numbers, right? Don't if I do something more and more, doesn't it get closer and closer to the right answer? That's this. You take a larger sample size, all these guesses are going to get closer and closer to the right answer. So a larger sample size will help you get there. All right. In fact, I have a formula for you. I can actually figure out how spread out these guys are. And this is the formula which we are going to use to figure out how spread out all those X bars are. The formula is, this is the symbol for it, how spread out are all those X bars. It's going to be the standard deviation of the population divided by the square root of the sample size. This formula should make a little bit of sense to you. What happens when you have a fraction and you increase the denominator? What happens to this number as you increase the denominator? Isn't that going to get smaller? Isn't that what we're saying here? If we took a bigger sample size, wouldn't all these guys get more bunched together? Wouldn't the standard deviation get smaller? So that should kind of conceptually make sense to you. What do you guys think of that formula? Last period said, hey, wait a minute. Okay, this formula, yeah.
And then doesn't the standard deviation equal square root of n?
What's that?
It's like
something else. All right, somebody last period said, hey, wait a minute. Okay, you gave me the formula of how spread out these guys are. But in your formula, you're giving me something else I have no idea what it is, right? Do I know how spread out these guys are before I start a problem? Then how in the world are you going to have, if I don't know what these are, how in the world am I going to figure out what this is? Is that a reasonable question? It's a crazy formula.
Your last period asked that?
What's that?
Your last period asked that?
Yeah, last student last period asked that. They didn't like that formula. They said, well, how? Great. Now how am I supposed to figure this out if I don't know what this is? Okay. Well, I'm going to answer that question for you in 2 weeks. Wait for 2 weeks and I'll explain it. But in all the problems that you're going to do for this chapter, they're going to give you this value. Okay, so they've got to give it to you in order for you to use the formula. But it doesn't really make sense in real life, right? If I want to figure out the standard deviation, the spread of the sampling distribution, well, I've got to use something in the formula that I have no idea what it is. Right? So that kind of makes sense. All right, I have one little caveat here. This formula only works in a given situation. This formula only works if your sample size isn't too big. If you take too big of a sample size, we got to use a different formula. Now, you're not going to be asked to memorize that different formula, But just understand, this is the formula that works only if your sample size isn't too big. And here's the rule we're going to follow. Our sample size needs to be less than 10% of the population size. Let me get the color coding going here. So our sample size needs to be less than 10% of the population size. So for example, last night, wasn't our population size 10? And didn't we take a sample size of 2? Not going to work. Right? 2 isn't less than 10% of 10. 2 isn't less than 1. So that formula didn't work on this problem. But in the real world, you're never going to get a sample size that big. I mean, how many people are voting? Millions. You're never going to get more than 10% of the whole population size. And the cancer situation, how many people could have cancer? That's kind of infinite. So you're never going to reach this. But just understand that this formula, we can only use this formula if our sample size isn't too big. And that's something we're going to check out before we start doing these problems. All right, I got another one for you. This one's kind of weird. How spread out all those blue guys are has nothing to do with the population size. How spread out those blue guys are, remember you've got one of them that you're on television with, but how spread out they are have nothing to do with how big the population is. I mean, in this formula, do you see capital N anywhere in this formula? Anybody see it in there? No. So how spread out these guys have nothing to do with how big the population size is. Well, what does that mean?
It's still just an S.
Well, think about this now. Here's what it means. Let's say I'm trying to figure out who the next mayor of California is going to be. Next mayor of California. The next mayor of Elk Grove. Okay, so I'm trying to figure out, I want to do a poll, and I want to figure out who the next mayor is going to be before the election happens. So I don't know, Elk Grove's got 200,000 people, let's say. Or I'm trying to figure out who the next president of the United States is going to be. What's the population size in that one? Millions and millions and millions, right? So in one situation, how big the population size is millions and millions and millions, and the other one, the population size is 200,000. What it means is this. Let's say I go take a sample of 200 people. The accuracy of my poll, the accuracy of my guess, will be exactly the same no matter whether I'm trying to predict the mayor of Elk Grove or the president of the United States. I mean, wouldn't you think that, oh geez, I got to figure out the president of the United States, I better take a bigger sample, right? There's way more people that I got to sample if I want to get close. And if I'm only doing the mayor of Elk Grove, I probably don't have to take as big a sample. No. How accurate, remember, you're going to get one of these guys. They're going to be the same exact spread out, whether you're doing the President of the United States or the Mayor of Elk Grove. You guys have a question on that? Okay, if the book gives an explanation, I read it every year. I don't know if I understand it, but every year like 2 or 3 students go, oh yeah, that makes sense, so I'm going to read it to you. It's on page 498. See if this helps you out a little bit. Why does the size of the population have little influence on the behavior of the statistic from a random sample? To see that this is plausible, imagine sampling harvested corn by thrusting a scoop into a lot of kernels. The scoop doesn't know whether it's surrounded by a bag of corn or the entire truckload. As long as the corn is well mixed, we've got to make sure we take a random sample. The variability of the results depends only on the size of the scoop. The fact that the variability of the result is controlled by the sample size is important if you're supposed to go do a poll. A statistic from a simple random sample of 2,500 people from all the residents of the United States will be just as precise. And what precise means is these guys will be same close together. The good dartboard or the bad dartboard, it's the same dartboard. Whether you're doing a sample from the whole United States or you're taking a simple random sample from San Francisco. The good news for designers is that in national samples, you can get the same accurate information that you'd get from just doing San Francisco. Now the bad news is if you're doing a small a small place like the Maryville Grove, you've got to get the same kind of big sample you'd get for the whole country to get the same accuracy. Is that scoop thing making sense to you? But the bottom line is that the accuracy of your guess, what do I mean by accuracy of your guess? I mean, if these guys were all like 20 and 12 and 35 and 2, man, they're so variable, you're not real sure about the accuracy of your guess. But what I'm telling you is you get the same dartboard for the same sample size, and I don't care if you're doing the whole United States or just the Maryville Grove. Okay? All right, so now we have a formula that tells us how spread out all these X bars are. All right, finally the last thing, the shape. Now shape is going to be a big deal here. And I'm going to have about, I don't know, 3 or 4 rules from you here that you've got to remember them all. Okay, here's the first rule that I'm going to give you. If the shape of the population distribution is normal. So in other words, that bucket, I don't know where my bucket is. But if I took all of those names, links, and I drew a graph of them, and the graph turned out to be normal, then the shape of these guys is also going to be normal. So in other words, if your original data came from a normal distribution, when you get all these means, it's going to have a normal shape too. So in terms of pictures here, if the shape of the population distribution is normal, then the shape of your sampling distribution is also going to be normal. So now we have an understanding of the center, shape, and spread of all of these possible sample means that we can get. And we don't have to go find them all, which is obviously impossible. Questions or comments? Okay. All right, got it.